right. So today we're talking about randomized algorithms for the first time this semester. These are algorithms that deliberately add randomization. You might wonder, why would you want to do that? So hopefully I can give you some examples where you can see some good trade-offs. Uh, and this is sort of fitting into uh, this theme of average analysis of graphs, and again, a specific sense of the word average. We previously did amortized analysis, which is always this like, that wasn't randomized, that was deterministic. And there's always saying, oh, after however many operations, in hindsight, it's always going to look like the average performance was good, even if individual operations might be bad, like you double your array, this kind of thing. Today's notion of average is maybe the kind of average you're used to talking about when you talk about things in the real world, right? So we're going to have an algorithm, and there's going to be some random coin flipping and things like this that alter the course of the algorithm. And then we'll talk about its average performance, typically average running time, uh, uh, as if you had run the algorithm like many times simultaneously and then measured the average empirically afterwards. Okay. So good, good. And again, what we are not doing is we're not talking about a fixed algorithm over a random distribution of inputs. That's a very different study and one we're not concerned with. Okay, so basically, here are the fun applications. We'll do a nice fun approximation algorithm for 3SAT, our favorite problem, and a nice sorting algorithm called quicksort. And then I'm going to introduce, like describe a neat algorithm called quickselect. But the analysis is kind of similar in many ways to quicksort, with some changes. So I'm going to leave that as homework with, some guidance. So you can test out what you learn in quicksort. And then the boring part is that, I'm going to have to like at least mention what these kind of mean. But I'm probably going to do it somewhat briefly, okay? And if you are not super comfortable with these terms, I'm hoping that maybe when we see it in context, that'll give you some practice. So the one thing I'm trying to avoid is turn this into like 20 minutes of me just defining things over and over again, and then you'll lose interest. So I might just try to get through the definitions and get back to the application. We could start using it. Okay, and then we can backtrack, double check our definitions and things like that. I just want to keep it engaging. And if you're still uncomfortable, it's written much more slowly in the notes, along with a lot of practice problems at the end of the chapter. Okay, there's like a list of 10 problems. They're just like kind of probability problems, just to help you practice with the definitions. And then hopefully, this isn't the only class we're doing this, so we'll get a little practice over a little bit of time, and over time, develop some level of comfort. I know that there's not enough time left in the semester to become super duper adept at it. That's okay. Just want to get some exposure to some ideas, to some themes, a little bit of practice. And if you really like it, you can take randomized algorithms or something. Okay, good. So let's start with 3SAT. So I don't need to remind you that I'm going to give you a formula, and there's going to be 3 variables for every clause. Okay, and we all know how important this problem is. It's really like a linchpin of this theory of NP completeness, in part because it's just so obviously expressive, and simultaneously so easy to check solutions for a computer. So we know that we probably can't get an exact algorithm for 3SAT. But I think it's quite reasonable if I give you a formula which is like roughly saying, here's a bunch of binary decisions, try to satisfy all these requirements. And you don't have an algorithm to satisfy all the requirements, but I could say, okay, can you satisfy as many as possible? Okay, And then also getting the exact max would be hard because that would be the same as figuring out if you can satisfy all of them. But maybe you can still approximate the optimum solution. So it's not MP hard to say, okay, I can guarantee that this solution, I don't even know what the optimum value is, but I can guarantee I'm within a factor of 2. So if there's some solution that can satisfy all M constraints, okay, here's an algorithm that'll satisfy M over 2. Okay? It won't tell me anything about whether or not the formula is exactly satisfiable. So it's not, risking solving all of life's problems. But it could still be very practical. It's sort of the best we can do under this regime of, oh, you can't actually compute everything you want to compute. Okay, so that's this. I mean, there's a whole field of approximation algorithms. This is just one example, just to get a little bit of exposure. But it's really I mean, the real point is about, it's a nice example of randomization, but that's the idea. So, okay. So again, trying to approximate SAT. I was supposed to, maybe I'll hide this a little bit. Approximating SAT is not necessarily MP hard, right? So does anyone have any ideas for an algorithm? Are you just given a SAT formula? No pressure to solve it exactly. Just trying to come up with heuristics that can try to satisfy a lot of clauses, and maybe we can also try to justify it. Yeah. Okay, so maybe you have some formula x1 to xn, and then I don't know, like you can maybe try to assign one at a time. So this is sort of some kind of greedy heuristic, and say, okay, of all the variables and all the configurations of x1 or not x1, xi or not xi, x10 occurs the most. So setting x10 to be true will satisfy the most clauses immediately, and then I'll figure out the rest from there. Then I have some remaining formula, figure out the kind of next best single choice, keep going. Okay, so this algorithm shouldn't work, but I'm trying to think of a good counterexample. Yeah, can anyone think of a counterexample for this greedy algorithm? So it should be something where taking the obvious choice is bad. Okay, well here's maybe one thing for like a 1/2 approximation. So maybe I have a variable x1 that appears in a lot of clauses, or and I'll have x1 bar also appear. Sorry, I didn't sleep well and my eyes are bothering me. You guys are all kind of blurry to me today. And what I'll do is I'll make x1 appear slightly more often than x1 bar. And then somehow I'll configure it so that like maybe all of these clauses are super easy to satisfy. Like maybe they all just have like x2, or there's some other way to really easily satisfy like some variable x2. And then this will be some relatively difficult thing. And yeah, try to make this kind of impossible to satisfy if I don't take x1 bar. Which I guess the easiest way is I can just have clauses with one variable in it. Right? I can just have one variable clauses. So I can just add a bunch of x1 bars that you won't satisfy if you take x1. Right? And then make these relatively simple to satisfy. So anyway, you're going to regret not picking x1 because x1 bar was really critical to a smaller number of clauses. Okay, so well, one thing that kind of comes out is maybe deterministic heuristics seem tough because as a SAT formula designer, if I know your algorithm and maybe more on my toes and really clever about SAT, I can try to figure out how to trick your algorithm into making the wrong decisions, right? Because SAT, you can express a lot of things. Okay. All right. So how about a sillier? Yeah. Yeah. So average hasn't entered discussion yet. What I want to argue is that for any particular, the worst case formula you give me, let's say alpha is 1/2. I'm trying to get a 1/2 approximation. I will get at least 50% of the best possible for any given formula. Yeah. So still worst case in that sense. So we'll never deviate from worst case inputs in this class. Arguably something like ML is the study of non-worst case inputs, right? Something coming from a fixed distribution. Okay. Um, good. So if we're a little bit pessimistic about clever sounding deterministic heuristics, what might be a sillier idea for say 3-sat in particular? Yeah. What if we, for every single decision, instead of cleverly counting, should I set excellent to be true or false based on some current point of view, what if I just flip the coin? Okay, so I flip the coin, and if it's heads, I'll assign it true, and it's false, I'll assign it. If it's tails, I'll assign it false. Right? This is the most ridiculous algorithm ever. You don't even look at your formula. Right? So this is not, in many ways, it seems like a ridiculous algorithm. So that's the algorithm we're actually going to study. Okay? For every variable, you're going to set xi to be true with probability 1/2, xi to be false with probability 1/2. Okay? And it'll be independent. That does matter. So different coin tosses for each one. We'll clarify the meaning of that in a moment. Okay. So we will do two things. For 3-sat, we're going to show this gets you a 7/8 approximation. That's not bad. That's like way higher than our curves on the exam and stuff, right? So like so 7/8 is not bad. And not only that, after we get through analyzing the 7/8, which from the right perspective won't be too bad, from the wrong perspective it could be a mess. We are going to take this algorithm, which was completely random, right? Completely random. I couldn't think of a more random algorithm, and we're going to make it deterministic. Okay, so that's kind of cool, and you actually come out with a deterministic heuristic. Okay, that is somehow making some kind of immediate decision based on the immediate information. It's going to make assignments one at a time, but the strategy will be kind of clever. All right, so that's cool, and maybe what's more amazing is that it's actually MP hard to do better than 7/8 for 3-sat. Okay, so this is a spectacular result that was proved in the 90s. So definitely after finding that out that this whole MP hardness thing was going to be an issue, there was a lot of hope for like, oh, that's okay. I don't need exact answers. I'll just keep getting better and better approximation algorithms, right? And approximation algorithms start coming out for various problems. They get better and better over time. So the idea that there are limits to approximations is a very consequential thing, right? And this is very hard to prove. This is far beyond the scope of our class. In a randomized class, I at least give a little bit of context and we get to some aspects of this proof. But so for 3-sat, what does this say? This coin flipping thing, which is like the most nonsense algorithm ever, gets you 7/8, and it's the best possible unless p equals np. Right? What does that tell you? It's like, okay, you really can't do anything with 3-sat, at least from a certain worst case analysis point of view. Right? So that's quite a strong, sharp statement. Okay, good. So that's one application. Oh, so what I'm going to do is I'm going to go through the applications first, try to get everyone really excited about probability, then get through the definitions, and then we'll go back and go analyze the algorithms in detail. But first, I want to present the algorithms because the algorithms themselves, I think, are already appealing. Even without the analysis, there's, I think, some interesting qualitative observations. Okay, good. So now let me talk about quicksort. Okay, so I also need not remind you about sorting. If I give you n comparable items and you want to sort them, and in increasing order, you know how to do merge sort and n log n time. You probably knew before the class started how to do n log n time with merge sort. We also did the lower bound. You can't do better than n log n, right? From this sort of query complexity. Okay, so good. So quicksort is a ridiculous algorithm. Okay, so you have a bunch of numbers, right? And so what we're going to do is, as a first step, I'm going to pick one of the numbers uniformly at random. Just pick one of them uniform, not arbitrarily, not like the first one in the list. One of them uniformly at random. Okay. And then I'm going to make two piles. The numbers that are smaller and numbers that are bigger. Okay. And I'm just going to recurse on both sides. So pick a random number, make two piles, figure out the two piles, and then concatenate them together, right, around your middle one. So this is sometimes called a random pivot. And already you can see that like the code is much shorter than merge sort, right? Because we've all done this before, like the merging step, you have to go from I from 1 to n and j from 1 to n. You keep comparing them. And then when you get to the end, okay, there's some items left in one of the lists. You have to make sure you include that part and things like, it's like nonsense. So, okay. So maybe a picture to describe this, right? This is maybe more intuitive of an algorithm. So you start with a bunch of numbers. You pick one of them randomly, okay? And then you're going to use that and divide it into two piles. They're not necessarily like even the way I've drawn it, okay? But okay, here's all the numbers smaller than that number, which we sometimes call the pivot. Here's all the numbers that are bigger, okay? And then we recurse and we sort the two sides and glue them back together. Okay, so I think, yeah, this is very intuitive. Yep. And we'll show two things. One, that it's going to match merge sort and expectation, and we'll more precisely define what it means to be an expectation, but it's kind of average running time. And not only that, but it won't actually be hard to show that it'll be at most n log n with really high probability, right? So that means it will be something like the probability that the time, I guess I haven't introduced this notation yet, is more than, I don't know, 10 n log n, is at most n to the minus 10 or something, okay? And if I made this constant bigger in front, this exponent will be bigger. N to the minus 10 is really small, right? So it's just dropping really fast. It's especially dropping for large n's, which is what we're interested in. So this is as good as a sure thing. Okay, I should also remark that this algorithm works very well in practice. There are times when Unix sort, the sorting library, just use quicksort. And I think that can be explained by the fact that the algorithm is very simple. So if you really did work out like the hidden constants for a particular architecture, you would expect it to be pretty small because it's not doing that much. Okay, good. Okay, and then the last thing then is to at least present this quick select algorithm. So again, we've done this before. So this is just like selecting the median, selecting any other rank element. I give you n numbers not sorted. Give me the median. Give me the rank n over 10. Give me the whatever. And as we know, you can sort n log n, but you can do something more clever that we did together and get it down to big O of n, right? But I'm sure your memory is the same as mine. It's not that easy to get big O of n. It was very clever. We had to do this median of medians trick. We had this funny recurrence, which was probably the most like not asymmetric recurrence that we've seen all class in the lecture. And so you can do it, and it's remarkable, but it's not easy, right? It wasn't obvious, and actually people complained that it's not super fast in practice. Um, so here's maybe something that should be appealing to you because it's much simpler. You should ask yourself, like, why did we do it the other way? And okay, so what? Okay, maybe you guys can guess. So given what you've already seen, what would be a different algorithm to try to do a selection algorithm? It's going to be randomized. So you want to find the median. Yeah. Perfect. So yeah, so the intuition is something like, you want to do something like divide and conquer. Maybe just to pick an item uniformly at random. I'm hoping it's close to the middle. There's a 50% chance it's in the middle 50%, right? And then I'll make the two piles and look at my element and say, okay, is it too big or too small compared to what I'm looking for? And then go into one of the two piles accordingly, right? So I think this algorithm is very intuitive. So you pick a random pivot, you split it into two parts, and then once you split into two parts, you can say, oh, I know the rank, right? So if there's like 100 elements here, they're not sorted yet, but I know there's 100 over here, then I know my pivot is rank 101. It's the 101th smallest element. And I can compare that to the index that I'm looking for, right? And now tell me if I should go to the left or to the right. And so you recurse on the appropriate half, and you find the element you look for. Obviously, when you recurse on the big side, you need to update the rank, right? Because you're supposed to, if you're removing 100 elements, you're looking for k minus 100 on the right side, things like this. Okay, so good. So I think this algorithm is much more intuitive than the median of means algorithm. And this one definitely works faster than the other in practice. This is not debated. I don't know why I wrote the algorithm in pseudocode. But we'll show that this also takes linear time, but in expectation. Good. I guess you will. So I think we'll give you two different choices on the homework, and you can choose which approach you prefer. Okay. Good. Good. So let me do some of the formalities. Okay. So let me define some of these things for us so that we have something to talk about, and bear with me. I'll try to make it as entertaining as possible, given that we need to get through some definitions, just so we can do the analysis, in appropriate context with appropriate definitions correctly. Okay, so, all right, who's seen this movie? Wait, really? Okay, well, you theater, but okay. So, uh, if I flip a coin and say it's in the air, and I say, okay, is it heads or tails? Right? What would you say? Like, yeah, okay. Well, I guess what I meant to say is like you don't really know if it's going to be heads or tails, right? The outcome at that moment in time is uncertain. Okay? You might say something like, oh, it's going to come up heads half the time. This is something we say all the time, right? I think you're very comfortable saying that it'll come up heads half the time. Okay, I think there's no ambiguity there. But like, what the hell does half the time mean, right? There's only one coin. It's impossible to get half heads, right? That's nonsense. It's happened once. Never mind. Okay. There's only one coin toss, right? So Yeah, once I was I had two friends who were calling heads or tails, and I called side, and then it rolled around on the floor, and it got jammed on the side, and I won. Okay. Uh, okay. But there's only one coin toss, right? So how do we talk about this? How do we formalize this? This is obviously not something that you're uncomfortable with. This comes up all the time, right? So all I want to do is put some notation, some formalities around something that should be intuitive, or at least shouldn't be too troubling if you don't think about it from the wrong perspective and you think about it from the right perspective. Okay, good. Okay, so formally in probability theory, you sometimes talk about events. Something happens. An event is like the coin came up heads. Okay, and there's some probability assigned to it. Okay, for every event, there's an event of it not happening, the opposite event, and that'll have some probability, and they must sum up to one. Okay, so you're assuming some world where any event will happen or not happen. Okay, if you want to question this premise, it's outside the scope of this class. Okay, so good. So we have some kind of events. We assign values to them called probabilities. You can have certain combinatorial things over events. So if I have two events, I can talk about, oh, okay, here there's an event where they both happen. It's called event A and event B. Or at least one of the two happen, event A or event B. Okay, so you can talk about these things unambiguously. You can take like a 2x2 kind of table and get any two events, you can kind of divide it into four-part possibilities. Both the events happen, only A happens, only B happens, neither A nor B happens. Okay? And those are the only four possibilities out of the combination of two events. Okay? And that means that these probabilities are going to sum up to one. Right? I don't know why I didn't write that, but these will sum up to one. Okay? Good. Okay. Right. So what's going on here? Okay, so if I have two events, right, two coin tosses, within event A, so I already know A happens, and beyond that, B could happen or not happen. Okay, so probably A happening is going to be the sum of both happening or A happening, B not. Okay, and what we can do is, so conditional probability will just be formally defined as the probability of both of them happening divided by the probability of A happening. So, okay. So one thing nice is that if I took this first formula, saying, okay, if A happens, either B happens or it doesn't, and divided by probability of A, I'll get one on the left, and I'll get these two conditional probabilities on the right. Right? And so now these look like almost events in some mini universe, adding up to one. Right? So it's like in some fixed alternate universe where A had happened, there's some remaining probability of B happening and some remaining probability of B not happening, but one of the two has to happen, and they sum up to one. Okay, so this is called conditional probability. Again, I think a lot of this is intuitive, but then we write down the rules, and then sometimes you're going to come into more non-intuitive situations, and then you got to stick to the rules. And then you can come up with like interesting, surprising results and expand your imagination that way. Okay, so in general, the conditional probability, so knowing that event A happens can affect the probability that B will happen thereafter. Okay, so if A and B are like, both heads for the same coin, of course, B only happens if A happens, right? It's complete dependency. If I knew A, I know everything about B. But in general, they're not different. We say A and B are independent if the two sides are equal. Finding out that event A happens doesn't tell you anything about whether event B is going to happen. Okay? And so if you work through some of the equations that we had before, which are all just things adding up to 1 and things like this, you'll find that all of these are the same and equivalent to independence, right? So for example, the probability of A and B happening is equal to the probability of A happening times the probability of B happening, right? Things like this, things you've seen before. Probability of B conditional on A is equal to probability of B. The conditioning on A doesn't give you any information. Okay. So that's fine. Okay, what am I writing here? Okay, so when I'm looking at the union of two events, good. Right, A or B. So within the event of A or B happening, I can either have only A happen, only B happen, or exactly, or both happens. And they're mutually exclusive. So that's what this identity describes. And okay, so it's not hard to show. So the way to think about this is sort of like a Venn diagram, right? It's actually, if you did the formal measure theory, this is roughly what it comes out to anyway. Imagine you're throwing like darts at a dartboard. Okay, one section is labeled event A, some section is labeled event B. Okay, and there might be some overlap. So if the dart lands on the overlap, event A and event B happen. If it lands on just the A side but not B, only A happens. If it lands on B, okay, so I have A, B, A and B, and A, oh, and then this whole thing, the union will be A or B, okay? And just like adding up Venn diagrams, kind of the area of A or B plus the area of the overlap will give you the area of A plus the area of B, okay? So that's what this equation expresses here. The probability of A or B happening plus the probability of A and B happening is always equal to the sum of probability of A plus the probability of B. Okay. Good. One thing really useful is the following. So if you drop out, this is already always greater than or equal to 0. And if you drop this term, you're going to get something called the union bound. It just says the probability of A or B happening is at most the probability of A happening plus the probability of B happening. Okay? From a Venn diagram picture, this is not very interesting, right? The size of the union is at most the sum of the two sizes. What's really powerful about this, we'll see this, is that I don't need to know anything about A and B to apply this bound. So A and B could have a lot to do with each other. They could have nothing to do with each other. Okay? A or B may be describing a relatively complex phenomenon, right? If you're just seeing a light bulb that turns on, if A or B turns on, right? It might be hard to discern the pattern. Okay? But it may be that A and B are relatively easy to analyze by themselves when you're not worried about how they're interacting with each other. So you'll be able to get bounds for A and B. That'll give you some bound for A union B. So this is going to come up because we are going to have, when I first learned probability theory, they give you these problems that were like, oh, you roll some dice and this happens, right? And it's like, some word problem and you kind of work out these things and things like this. We are going to be looking at algorithms that are flipping coins, and it's running for n steps or n squared steps. And, you're picking random pivots. If you pick a random pivot at the beginning, how does that affect your choice of pivots later? It's way more kind of dynamic, and not only that, but eventually you also want to get to a point where you're designing randomized algorithms too, right? And you're not going to want to map out a lot of the fine-grained details like I was first trained to do when I first learned probability. So something like this, where maybe A and B are relatively easy to extract from the description of your algorithm, even though what you're actually interested in is an A union B, and you can bound it, right? These simple bounds are actually really powerful in the randomized algorithm scenario, at least more so than I appreciated when I took probability classes kind of by themselves. Good. All right, sorry, this just doesn't end. Okay, so the next set of definitions has to do with not events, but random variables, which is things that output quantities. Okay, like a dice, 1, 2, 3, 4, 5, 6. So saying that this random variable x took the value 5 would be an event. Okay, but the real key feature here is now we're talking about quantities. They can be added together. So yeah. I guess they don't have to be. Okay, you can do heads or tails. But the point is you have some variable and it takes some kind of discrete value uh, or continuous, but we won't talk too much about continuous. Okay, so yeah, so silly example. Okay, if x is modeling the outcome of a dice, it's going to be one of the 6 values 1 through 6, each of them with equal probability 1 over 6. Okay, good. Now, just like with events, you can start looking at combinations of random variables, right? You know, you model 1 dice as a random variable, or you can model 2 dice with random variables. And so I can always take 2 random variables that are taking, different values, and then I can think of that as one value with kind of 2 coordinates, right? One random variable. So you can talk about x, y would form another random variable, at least formally speaking, and then you can take combinations of values. Okay, so you can always kind of combine events. In general, the probability of, one coordinate being one and the other coordinate being another, simultaneously is not necessarily equal to the probabilities multiplied together, right? So if x and y are both the outcome of the same dice, then of course this doesn't hold, right? Because only 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6 are possible. They're not. So when it is the case, then you say the random variables are independent. You've probably seen this to some extent before. Okay. Yeah, okay. Same coin, different coins, not so interesting. Okay, here's maybe the most important part. Okay. This is where the word average finally enters the picture. Okay. So for a random variable x that's taking some quantitative values, the expected value of x is I sum up over all the values it can take, that value times the probability of taking that value. This should completely coincide with how you think of average over any set of things. Okay? So, good. Okay. Here's maybe the most important thing. If I had one goal in when we discuss randomized algorithms, if there's one thing I wanted to emphasize and really get across, is the importance of linearity of expectation and the power of linearity of expectation. It says, if I have 2 random variables, x and y, the average of their sum is equal to the average of x plus the average of y. So the average of the sum is the sum of the individual averages. Okay? And it's exact. This is not like less than equal, it's greater than equal, or anything like this. It's exact. Okay? This is useful for the same reason that union bound is useful. I don't need to know anything about how x and y are related to apply this theorem. Okay? So for us, x plus y, there's going to be a lot of random variables here. It's going to be more than just 2. This can, if you can do 2, you can do 3, you can do 4, you can do 5. There's going to be a ton of things in here, and the whole sum might model the total running time of your algorithm, which has to do with a bunch of the individual decisions, right? And those individual decisions all depend on each other in all sorts of screwed up ways. You don't even want to think about it, right? But this says, oh, you can separate it out and analyze each step in isolation, right? And so you can take some kind of crazy, adaptive, randomized, who knows what it's going to do algorithm and actually break it down and be able to analyze it. And you don't lose anything. It's equality, right? So average, looking at the average, studying the average is a knife through butter. Okay? You will be able to make statements about the average of something, and you won't be able to say anything else about the phenomenon. Okay? So average is like really, really, really useful. That obviously extends far beyond algorithms. So hopefully maybe algorithms will give a place just to practice this thought. Okay? So average is, I think just getting an appreciation for the word average is maybe the goal of this week. Okay. Uh, you can have conditional expectations. So if I knew event happen, A happens, then what's the remaining expected value, right? You might go into the midterm having some expectation of what the average score is going to be, and then you come out the midterm, you talk to some of your friends, you find out, oh, that was a DAG. Your conditional expectation has changed, right? Because you know that that was a DAG or something. Good. Um, so you can verify this, right? So assuming you're kind of rational, your expectation going into the test for your score should be or coming out immediately after the test, the expected value given it was a DAG times the probability it turned out to be a DAG, plus the expected value if that problem wasn't a DAG times the probability it wasn't a DAG. Okay, and then but you can just plug this in and check for yourself. Okay. Good. Um, yeah, you can take expectations over multiple random variables. So this is just, two random variables, x, y. There's really not a strong distinction between multiple random variables and one because you can think of multiple as, kind of coordinates of one. But you do have something called the law of iterated expectations. So if I have two random variables going in, I want to know the expected value overall. I can take the expected value of x and the expected value, over the remaining y conditional in x. So that's like finding your information out piecemeal. So x is finding out the problem is a DAG, and then y is finding out that there's some connection between partition and shipping containers. And, each bit of information you get, there's some inner expectation that updates, right? But overall, it'll come out, yeah, the same. Okay. Yeah, I guess here's something I found on the internet. I think from some stats class, and maybe this is in all of your stats classes. If X is whether or not it rains tomorrow, and Y is whether or not it rained today, and you're really interested in you already know if it rains today, and you want to know X given Y, or rains tomorrow. Oh no, sorry. Okay, so this is maybe yeah. Okay, if you know the probability of it raining today, and you know the probability of it raining tomorrow, given it rains today, then you can work out the probability of it raining tomorrow. Okay, good. All right, here's one last thing. It won't come up today. I guess not much will come up today. Um, so this is called Markov's inequality. Okay, so this is one way to write it. Another way to have written it is like this. Probability of x greater than or equal to alpha times the expected value of x is at most 1 over alpha. So that seems technical, but let me say it out loud. The probability, let's say that the average midterm score was lower than 50%, or else this wouldn't be so interesting. It's possible. Okay. Now, the claim is that the probability that a student got more than twice the average on the midterm can be at most 1/2. Or let me put it away. At most half the class got 2 times the average score on the midterm. Is that obvious? Some find it obvious, but some not necessarily. So if you found it obvious, why? The lowest possible is 0. So if more than half the class got 2 times the average, that would increase the average, right? So if the average was 40%, 2 times the average is 80%. And if more than half the class got 80%, then suddenly the average would be bigger than 40%. Okay, so that's all Markov's inequality is saying. Okay, the fraction of the class that's more than alpha factor greater than the average is always at most 1 over alpha. It can't be bigger because you can only fit so much into the average. You can work this out with the definitions. It's not, you know, uh, so bad. But you know, so this looks fancy, but actually, and seems to have a fancy name, but actually, it's almost common sense. Okay, so let's get the proof. Okay, so what I can do is I can start motivating an analysis, and then we'll really make some headway next time. So let's go back to 3-sat. The goal is to get a 7/8 approximation for 3-sat. Okay, which amazingly is the best you can do. So, okay, so let's try to analyze this thing directly. Here's a formula with one clause, and suppose I assign x1, x2, x3, you know, to be heads or tails uniformly at random by flipping, true or false by flipping coins. Okay, what is the probability that I satisfy this clause? Or maybe let me reframe it. What is the probability that I don't satisfy this clause? 1/8. So x1 has to flip tails, x2 has to flip tails, x3 has to flip heads, right? So that means the expected value of the number satisfied, well, there's one that's satisfied 7/8 of the time, right? Okay, good. Okay. What if I had two clauses? This isn't, so these are two clauses that don't share any variables. What is the expected number? Oh, yeah, so, okay, so if I have two different clauses, so what's the probability of, okay. So if we worked it out exactly, right, the expected number of satisfied clauses is going to be, I guess, 1 times the probability that you only satisfy the first one, so that's E1 and not E2, plus 1 times the probability that you don't satisfy the first one, E2 times 2 or something, right? This is just writing out the definition of expected value. Okay, so what is the probability that I satisfy the first clause but I don't satisfy the second? So I know they're independent because they don't share variables, so I can break them apart. This is going to be like 7/8 over here, and then 1/8 over here. And then 7/8 over here times 1/8 over here. And then 7/8 times 7/8 times 2. Okay, I've done the math ahead of time. So this should give you 7/4. Okay, so to give a little bit of appreciation for what comes next, suppose I made it a little bit harder and I made them share just one variable. Two clauses, they're sharing one variable. Okay, so I can write down where we left off before. I have this probably E1, not E2, which is not satisfying the second one, probability of not satisfying the first clause, but I satisfy the second one, plus 2 times the probability that I satisfy both. Right? There I'm just working through the definition of expected value. Okay? So like, what's this one? So probably I satisfy this clause, but I don't satisfy this one, the second one. So I guess like, okay, if x3 comes up heads, then actually I won't satisfy the second one, because this will also be satisfied. If it comes up tails, that's just 1/2 probability. Now I have a 1/2 chance of satisfying this one, and then I guess a 1/2 chance of not, oh no, 3/4 chance of satisfying this one, and then 1/4 chance of not satisfying this one. So what was that, like 1/2 times 3/4 times 1/4 or something, right? The point is, like, it's getting a little more complicated. All I've done is have two clauses overlapping at one variable, right? And if we just have, like, imagine we have three clauses, right? Like, if we had time to work through this, thank goodness we don't. It would be very painful. And if I just add like a third clause, it's already game over, right? Our head breaks. So that's where we're going to leave off. You know, we have these algorithms and these formulas where you have lots of interacting things. That's why they're complicated. That's why they've always been complicated, right? The clauses are overlapping, one bit flipped here, that affects things over there. It's a big mess. Okay, so when we come back next time, we're going to figure out how to deal with this general situation. Okay, all right, thanks, guys. So let me remind us what we started last time. So we were talking about randomized algorithms. This is again the second part of this two-part theme on quote-unquote average case analysis of algorithms. One sense of the word is amortized, you know, average always in hindsight. The other is average over kind of random decisions made by the algorithm. And a really strong distinction again is that we are not averaging over inputs. Still worst case inputs, robust algorithms. We're not letting any of that go. So the idea was that I had three basic applications to try to inspire you. One of which is, you know, analysis kind of similar to Quicksort, so I'm leaving for homework. And we went over that, and then I gave you a bunch of definitions. So let me just skip everything we did last time, because as we now discuss the problems in details, I'll have to reintroduce them. So, good. Takes a while, doesn't it? Okay, so here's where we left off. So we were looking at 3-SAT in particular, and trying to get a good approximation algorithm. And we had some discussion. Some ideas was trying to do like basic greedy heuristics, but that seemed a little bit troublesome because once you kind of fix a heuristic, it seems like, okay, I have a lot of freedom in making a SAT formula. I can try to kind of work my way around this. So we started looking at what I called a silly algorithm, which is for every variable, I'll flip a coin. If it's heads, I'll set it to be true. If it's tails, I'll set it to be false. So we're going to show that this is a 7/8 approximation. That means it gets at least 7/8 the fraction of the optimum solution, no matter what, on average. And then we'll take this completely random algorithm and we'll turn it into a deterministic algorithm. You don't actually need coins at all. But it'll be inspired by a randomized algorithm. So I think that's really neat. And again, the amazing thing is that this, you know, relatively naive algorithm, which doesn't even look at the structure of the SAT formula, right? It's just like, no matter your input, I'm just going to do the same thing. It's an oblivious algorithm. It's actually the best you can do unless P equals NP. It's almost like you can't extract any information in some kind of worst case sense unless P equals NP. So that, you know, proving this is very, very hard. I've never even really gone through all of it, at least to get a sharp constant 7/8. But just the statement itself is enough to ponder. Okay, so we started analyzing the algorithm, and we're trying to figure out, okay, what's the expected number of clauses that will be satisfied, the average. Okay, and we can start looking at these things directly. Like if I just have one clause, the only way for me to not satisfy it is if I kind of get tails, tails, and heads. So out of 3 coin tosses and 8 possible combinations between heads and tails for each, 2 cubed, only one of them is bad. So 7/8 is what we get. We can do something similar with like 2. Here I have 2 clauses that are independent, and that kind of makes the analysis a little bit easier. But what we're starting to get into was like, okay, what happens if I have even one clause in common, or one variable in common for 2 clauses? I feel like this is like the smallest non-trivial example I can give. Barely more than one clause, minimal non-zero overlap. And here you already need to start doing things like, okay, if x3 is heads, then what's the remaining outcome? And if it's tails, then what's the remaining outcome? And then combine it and things like this, because they overlap. I can't just break apart the clauses, right? And if you think that's bad, okay, what if I had three clauses or something, right? And there's more shared variables and things like this. It just like rapidly gets more nasty, right? And here we're looking at, very, very small examples. Of course, we're interested in large formulas, right? And then you're just like screwed. Okay. So the question is, how can we analyze this algorithm? So the basic kind of analytical issue we're facing is that all these clauses are, very strongly related to each other, right? It's really hard for us to detangle them. It's sort of the same reason why we couldn't figure out how to solve them deterministically to begin with. These SAS formulas can be very complex. Okay, so out of that explanation, I only liked one word. That was mean. So we'll stick with that. Okay, but I guess before diving in, I just want to mention that this is only a special case of a more general thing, right? How do we analyze a randomized thing with a combinatorial explosion of possibilities? I mean, we've always been dealing with combinatorial explosions of possibilities, right? Is it binary search kind of situation or not? Right? There's always been exponentially many paths from S to T, but sometimes we can pick out the shortest one, things like this. But now we're throwing the word random into it. Okay, so that's really what we're doing. Okay, so what are we going to do? Let's see. Okay, so the key idea is that I only want the average number of clauses. I really don't need to map out all the combinations. That's way more detail than strictly necessary. Right? Before we're looking at, okay, what if x3 is equal to true? Then and we kind of build out this tree of possibilities, which, the size of the tree is like the size of a brute force algorithm. It's a huge pain. Okay? But we only want the average that is a reductive aggregate number, right? You only need a small number of bits to describe the average. You need a large number of bits to describe all the full distribution. Okay? So, good. All right, so how are we going to leverage this? For every clause, I'm going to make a random variable yi. Okay? And all I'm going to do is say, was this clause satisfied or not? So I'll write 1 if the ith clause is satisfied. So you flip some coin tosses, right? So that's where randomness. And yi just reflects the outcomes of the coin tosses. So if the clause is satisfied, we output 1. If the clause is not satisfied, we output 0. Okay, so just yes or no. And what we're interested in, okay. And as we already did together, worrying about one clause was pretty easy, right? Looking at a clause separately, so I'm only unlucky if I get 3 straight bad coin tosses. So I'll get it right 70th at a time. So a single clause will be satisfied 70th at a time. That was super easy. That you already knew how to do. Now, what we're interested in, right, is the expected number of clauses that are satisfied. Okay. Now, if I don't worry about expectations, this number of clauses satisfied, that's just the sum of the yi's over all the clauses. Okay. So we'll write the sum from 1 to m of yi, right? So nothing has actually happened. I just kind of re-express things in a different notation. But now what? Yeah, so the expectation of the sum is the sum of expectations. So here we'll apply the fabled linearity of expectation. And what have we done conceptually? See, this is the expectation of a complex phenomenon, expectation of the total sum. I have no idea how to actually attack this sum directly in any fine-grained detail. This is the sum of expectation of individual separated out components. It's trivial to analyze each yi by itself. Okay. So what does this come out to? Yeah, 7/8 m, right? So this is actually quite easy. Okay. And that is the power of linearity of expectation, right? It's asking the right question that lets you separate out the components and makes the remaining analysis actually easy. But you have to look at it kind of sideways. You have to look at it in the right level of abstraction. Okay, good. Great. So that's how you get 7/8. Now, I claimed that we should be able to de-randomize this algorithm. Okay, so our algorithm is about as random as an algorithm from SAC could be. Every single decision was made into a coin toss, right? The question is, how do I turn this into a deterministic algorithm? Any ideas? Any hints of an idea? Yeah. Well, okay. So can we just set the first one to be true? Wait, so are you just going to set everything to be true? Well, somehow, so we have tried to come up with deterministic heuristics before, and it felt a little bit tough. And that seems like also another kind of relatively simple deterministic heuristic. Just make things happy or something. It feels like it wouldn't be hard to manipulate it to get a very bad overall solution. Uh, so it's got to be something a little bit more layered. It should be inspired by a randomized algorithm somehow. Yeah. Yeah. Okay. So that's good. You have another. Okay. Oh, okay. All right. I'll just keep going. But feel free to interrupt. Okay. So we are the keyword is going to be condition. Okay. So let me break out exactly I think what was being suggested. All right. So just for convenience, I've now introduced z to be the sum, so I don't have to write it over and over. Now we know the expected value of z is good, right? Now, okay, so what's that saying? If I flip coins for all n variables, an expectation I'll get a good solution. Okay? So if I break that into expectations, right? Okay, the expected value total sum was probably 1/2 I get heads for the first variable, and then there's some remaining expectation. Plus, probably 1/2 I get tails, and then there's some remaining expectation. So what does that sort of tell us? Consider your two choices are setting x1 to be true or x1 to be false. I'm claiming that one of these two choices must be pretty good. Why? No, they don't have to be equal. Maybe you do x1 to be true is worth more than setting x1 to be false. I'm claiming that at least one should be at least as good as Z by itself. At least one of these choices should get you 7/8 M, but why? All right, so here's your expected score. Here's your expected score if you set it to be true. Your expected score if you set it to be false. So your overall expected score is the average of if you did true and if you did false. So one of these must be good. If these were both less than 7/8 M, then this would be less than 7/8 M. So one of those two choices, this or this, must be at least this. Okay, so there's always some choice setting true or false that will not hurt your expectation, maybe even increase it. Okay, so one of those two choices increases your expectation. Okay. Good. Anything down here? Right. One of these two choices are good. Okay, but how do you figure out which choice is good? You know that your problem is just from the mathematics that one of the two choices are good. Yeah. So you're trying to make an algorithm right now. How do I actually figure out which of these two to take? Uh-huh. So we want an algorithmic. Yeah, I don't think you fully. Yeah. So let's try to get rid of the word heuristic. That just never works in this class, but I think you're on the right approach. You should be looking at the consequences. Yeah. No, no, because that would just fall back ultimately on the original greedy strategy. Yeah. Right. So we can actually calculate this directly because it's relatively simple. So, okay. What's here? So, if I look at this quantity, what's my expectation after it's true, right? And we apply linearity of expectation again, right? And so this is exactly what was being described. For each of these clauses, given that I've set x1 to be true, and I haven't flipped the other coins yet, what are the odds of it being ultimately true? So if x1 was in the clause, this is just 1 automatically. If x1 wasn't in the clause, then it's still 7/8. If x1 bar was in a clause, there's only two variables left. So it's like 3/4 or something like that, right? So you can just say, oh, well, what does the remaining formula look like? And what's my remaining expected value? You can just calculate it, right? Just based on how many variables are left in the clause, or if it's already satisfied, things like this. So you can write an algorithm that just scans through your formula, looks at each clause, see if it's already satisfied, and if not, how many kind of live variables, unknown variables are left, and then figure out your expected value. So you can get this exact number. And then once you have that exact number, you just keep going, right? So you can just compute them, and it won't be too hard, and you keep going. Okay, so you can do this by induction, right? So you just keep making choices one at a time while making sure your remaining conditional expectation is greater than the original one. Just take the better choice, better choice, better choice. Okay, and you just keep doing the whole thing. Uh, it just looks a little bit longer because there's k variables you're already conditioning on or something, but it's the exact same thing. I've already made k choices, and the k plus one's choice, one of the two has to be good, and you can compute exactly the value. Okay, so this is called the method of conditional expectations. So it's pretty cool. Because right, we've actually come up with a deterministic algorithm. It's not randomized at all anymore, right? But I think it would have been hard to come up with without thinking through the randomized experiment. The randomized experiment itself seemed complicated until we realized we were only focusing on the average, and the average lets you separate out complicated parts. Okay? That's I think the real point. Okay, any questions? All right, on to quicksort. Yeah, so here you're going to get 7/8 M, and opt is at most M, so you always get 7/8 opt. Uh, your algorithm will always, whatever opt is, that score, you'll always be at least 7/8 times that score. Sure, it can overshoot, but in the worst case, you'll get at least this. In the randomized case, on average, you'll get at least 7/8 of opt. Yeah, but regardless of the input, you always have this worst case bound on your quality. Okay, yeah, there may be very easy formulas, right? In which case, it's almost like, why are you doing this? You should just, look at it directly. But okay, all right. So now let's look at quicksort. Okay, so here again is the algorithm. I want to sort this unsorted array. I pick a random one, and I divide into two halves: the bigger half, the smaller half, and I recurse. So inside here, it's going to pick another random thing split in half, pick another random half, right? But as you know by now, there's no point in thinking it through. You just recurse, and you just put this thing back in the middle and concatenate the two lists. So I think this is much simpler than merge sort. Okay, although the analysis maybe is new for us. All right, so, okay. So some kind of like randomized divide and conquer-ish algorithm, right? So if I kind of try to do what we always do, and we write, T of n is equal to something, how would I write it? Like, I guess you don't really know the pivot, so maybe it would be something like, did I write ahead of time? So maybe it would be something like T of k minus 1 plus T of n minus k plus O of n, where k is the rank of the pivot you picked, is kind of like uniformly random. Right? This would be sort of an exact accounting. Big O of n is just because after you choose the pivot, everyone needs to be compared to it, so you need linear time. Okay, so and like, okay, how am I going to deal with this recurrence? And you can deal with this directly, but it's a mess. So anyway, just to build some intuition, okay. Ideally, what do you want your pivot to be? Yeah, like right in the middle, right? If so, you're always splitting in half and over 2 and over 2, kind of like merge sort. Um, what's the worst? Okay. So if you're always picking an extreme point, then you're going to lead to an n squared running time because you have n times n minus plus n minus 1, n minus 2, n minus 3. Okay. So, so ideally this would take n log n time, but it's not impossible to get n squared time. So in some strict sense of worst case, the running time could be n squared, right? And the question is, which one? And how do we think about this question, right? So this random experiment, there's a best case of n log n, there's a worst case of n squared. How do we think about it? And in general, with this algorithm, what are the consequences of choosing like a good pivot first and then bad pivot next or something, compared to choosing a bad pivot first and then good pivots after that? It feels like the order could matter, things like this, right? And early luck or unluck could affect downstream dynamics. So, okay, so that seems complicated. All right. So lucky for us, we're only interested in the expected running time. So again, if I pose a question like this, it seems impossible. Okay, because we can't map out all the possibilities. But what we can do is try to study the expected running time. So if I had on the same input run this algorithm a billion gazillion times, what would the average running time look like? Right? Which may be actually what you perceive if you use this algorithm on your computer, because you're going to keep reusing the algorithm again and again. Okay, so that means, I'll let my random variable is going to be the running time of the algorithm. Okay, and I want to find expected value of z, so for every possible running time, the probability of being that running time times the running time. Okay, so, any ideas of how to approach this? Yeah. Okay, so one thing you could try to do is you can take sort of that recurrence perspective and try to unroll it. Okay, it'll be a little painful. What we're going to do instead is, again by linear expectation, but it's going to be more slick. Okay, so we're not going to try to do the recurrence tree kind of thing, because that could be complicated. It's like 1 over n of a very lopsided tree and 1 over n of a slightly lopsided, it's a huge pain. So instead, what I'm going to do is I'm going to set up these very clever indicator variables. So for any two indices, or let's put it this way. So I'm going to look at which pairs of numbers are actually compared to each other. So many pairs aren't compared, right? Because you split down the middle, you make two different piles. The two different piles will never be compared to each other. Okay. So xij is going to be 1 if the I smallest element is compared to the j smallest one. Okay. And it's going to be 0 otherwise. So the sum of xij's is the total number of comparisons made by the algorithm, which is the running time up to a constant. Okay, good. So that's our setup. Okay, so now we're interested in this sum, the expected value of the sum of xij over all indices I and j. Okay. All right. So here's what I want, the average running time to a constant. What's the first step in the analysis? Yeah, linearity of expectation. That's often the first step, especially in this class. Okay. So we apply linear of expectation, and now you're looking at a sum of these individual xij's, and maybe it'll be easier to analyze an individual xij than having to think about the whole algorithm and all of its possibilities. Okay. All right, so anything down here? Yeah, so now we can just study xij by itself. Okay. How should I think about xij? All right, so since xij is a 0 or 1 random variable, its expected value is also the probability of it being equal to 1. So I'm really asking, what are the odds that the 100th smallest element is compared to the 200th smallest element? Okay. So how can we try to figure that out? So what are the odds that one element is compared to another? Yeah. I or j at some point has to be the pivot, right? Okay. Now, over the course of the algorithm, every element ends up becoming the pivot eventually. So that's not quite strong enough. So I have this set of elements, right? I think I have a picture down here. Yeah. Right? I smallest, j smallest. So it's true. Yeah. Yeah, so to refine that suggestion, if I pick a pivot in the middle, it'll split them up, they'll never be compared. Okay. If at this stage I picked I, then I would get compared to j, and if at this stage I picked j, it will get compared to I. So I and j are compared to each other if and only if one of them is picked as a pivot before anyone in the middle. Okay? So I and j are compared to each other if and only if one or the two other is picked as a pivot before any element in the middle. Right? So it's sort of like a game. Each round, there's some pivot. It's either among these critical ones or it's on the outside. If it's on the outside, you just get a new round, right? But then eventually, some pivot is picked from between I and j, possibly including I and j. Was that in the middle or was it not? Okay. So, good. Okay, so what is the probability that the I or jth element is selected as the pivot before any of the elements in between? Just in the entire algorithm. Yeah. Yeah, so the way we pick our pivot, it's uniformly random, right? So all these elements are equally likely to be picked as a pivot. No one's going to have a higher probability than anybody else. Okay, so it's all the same. Okay. So, I thought I had it written. So this will happen with probability 2 over j minus I plus 1. That's just counting the number of elements, including the edges. Okay, good. So that's our expected value. It sort of intuitively makes sense. Two items that are right next to each other are way more likely to get compared to each other eventually. I guess they always will, probably. And then really far apart, you're almost definitely going to split them up. So it is at least decreasing in a distance like you would expect. Okay, good. Okay, so now when we put everything together, I look at the expected running time. The first step is linear of expectation always. Okay. And then we start plugging in, right, I mean, this is really the most important conceptual step because now you've gone it down to analyzing one element, which while subtle, is still much more manageable than the whole original algorithm. And so you get this sum, which I'm just plugging in over all the i's and j's, 2 over j minus I plus 1. Okay, and then from here, it's just mathematics. So what I did was I rearranged the sum. So instead of like going from I from 1 to n, where I was a smaller one and j was a bigger one, now I'm going from j from 1 to n and I from 1 to, it should be j minus 1, but that's okay. Okay, so I rearranged the two summation terms, but otherwise we're enumerating the same things. So if you look at this one for fixed j, right, it's really going like 2 over j plus 2 over j minus 1 plus 2 over j minus 2 plus 2 over j minus 3, all the way down to, I guess, 2. So it's a decreasing harmonic sequence. So it's going to look, so this is an overestimate, 2n times 1 over 1 plus 1 over 2 plus all the way up to 1 over n. Really, for each j, this would only go to 1 over j, but we'll just throw in some extra terms. That's okay. Okay? So you just have a bunch of sums, and I feel like this has come up before, but I don't remember. What is the sum of these terms? Log n. Have we done that as a class before? Has that come up? Okay, so this is big O and log n. Does anyone know how to prove this? Or what's the easiest explanation for why this is about log n? But you've probably seen this fact before. Okay, so here's a trick that you won't forget, hopefully. Yeah, so this sum, 1 over 1 plus 1 over 2, right? You know, this is like some kind of Riemann sum. 1/2, 1/3, 1/4, 1/5, 1/6, 1/7 kind of thing, right? So it's awfully similar to this curve. Okay. Okay, I'm not doing a good job. So this kind of curve here, which is 1 over x. Okay. So the area under this curve is pretty good approximation of the squares. Okay. So this sum is about the integral from, I'll say 1 to n plus 1, 1 over x dx. And then you might remember that integrating 1 over x will give you the log. Log n plus 1 or something. Okay. So that's it. That's that way you'll never forget. So in general, one way to deal with summations is sometimes just estimate it was the integral. And you might be off by 1 or something because, you know, we've sort of shifted the squares over because I didn't want to integrate to 0 because 1 over 0 becomes painful. So, you know, there's some loss, but not much loss. Okay, good. Great. Ooh, we're finishing. Okay. Oh, okay, we have more work to do. Okay, good. Okay, so that's n log n time in expectation. The trick was to look at these indicator variables. Okay. And now I guess I'll do something maybe, it's probably the only time, I don't know. Okay, so now I'll try to do something a little bit fancier. I'm going to argue not only is it n log n an average, but it's exceedingly likely to be at most, say, 10 n log n or something. Okay, it's really not going to be much bigger than n log n. Okay, so which is important because you might be like, oh, well, it could still be n squared. And I'm going to say it's almost never n squared. Okay, there will be like 1 million solar eclipses during which you'll get struck by lightning every time before you get n squared for a sufficiently large n. All right, so okay, so the setup here is a little bit more intricate. So what we're going to do is, so over the course of the algorithm, there's all these subproblems with subsets of numbers, right? So I'll call those subproblems. And for a particular element E, I guess, I'm going to count the number of subproblems it's in. So it's like the depth of the recursion. Okay. And so if I sum over all e's, every time an element in a subproblem will get compared to the pivot. That accounts for all the comparisons. So if I sum up over all the DEs, I'll get the total number of comparisons. That's basically the running time. So that's the framing. A little bit different than what we did last time. Okay. And the claim is that any particular element is in at most 32 log n subproblems with probability of error at most 1 over n cubed. Okay, so some polynomial in n that's really small when n is big, which is the regime we're interested in. Okay. All right. So why is this bound useful? So we will prove this, and that'll take up the remainder of class. But let me explain first why this will give us this high probability running time that we want. Okay. So how can I take this claim? I don't know why I wrote why, but how can I take this claim and make it useful towards the original goal of bounding the total running time with high probability? This is sort of like saying with high probability any individual element is in at most log n or so subproblems. But I'm interested in all of them summed up. So I think what we're trying to argue is that every single E simultaneously is in at most like 32 log n subproblems. Yeah, so if this was true for all elements, then I just multiply by n and we'd be good. But we haven't shown that it's true for all elements. I've only shown that for any element is true with high probability. It doesn't tell me anything about simultaneously directly, right? So how can I argue that simultaneously they'll all be bounded? No, you definitely can't argue they're independent. Right? If you have a lot of subproblems, there's the same numbers in those same many subproblems. It's definitely not independent. Okay, so I want to argue that the maximum over all elements of this term is at most 32 log n. I want to argue this bound is small. This is saying that some element is in too many subproblems. I want to say this is small. Yeah. So in general, I make this constant bigger, and it would make this exponent bigger, is what we'll see in the proof. So there's some trade-off. Yeah. So I can make this a little bigger. And it's not a very tight analysis either. I chose a big, comfortably big number. Yeah, this could be smaller. It'll make more sense when we analyze that claim. Okay, I need to keep moving. So what we're going to do is we're going to apply the union bound. Okay, the probability of any of those elements being bad is at most the sum over all elements, that element being bad. This is the union bound. The probability of A union B is at most probability A plus probability of B applied to every element. Right, this is great because as pointed out, it's not independent or anything like that, but you can still apply the union bound. Okay, and so if I take this, how many terms are there in here? And each of these is 1 over n cubed. So you multiply that together, you still get 1 over n squared. Okay, so it's probability 1 over n squared is the odds that any element is bigger than this. So with high probability, that won't happen. And all of your elements are appearing in at most 32 log n subproblems. So your running time will be n log n. All right, let's keep going and make sure we finish. Okay, So all that's left now is this particular claim, okay, which I'll have to do a little bit quicker than I had originally planned. So we're going to fix an element E. I want to show that the number of subproblems it's in is not too bad. Okay, at most 32 log n. So we're going to set up this random variable, which is the number of elements in the subproblem containing E after in the ice kind of recursive call. So x0 is n, and x1 we're hoping is like n over 2. So we want to argue that x something gets down to 0 really fast. Okay. Good. Okay. Good. So as soon as E is selected as a pivot, xi is equal to 0. Okay. So d is greater than or equal to I only if xi is greater than or equal to 1. When xi is equal to 0, that means those subproblems have died off. E is not being in a real subproblem anymore. So d will be less than I. Okay, so what I want to argue is that xi reaches 1 with high probability. Okay, so we're going to first try to upper bound expected value of xi. And here's how we're going to do it. So of all the possible pivots, half of them are good in the sense that they belong to the middle half and kind of would get rid of at least 1/4 of the elements. So if I pick something in the middle 50%, there's 25% on each side, so I'll throw away at least 25% of the elements. Okay. Good. So, all right, we can work through this. What's the expected value of x1? Okay, that's the number of elements remaining in the first subproblem. Okay. And so for one way to reason about this sort of conservatively is say, okay, with probability 1/2, I get a good pivot and it goes down by 3/4, right? With probability 1/2, I get a bad pivot and maybe I don't make any progress, okay? Probability 1/2, it goes down to 3/4 n. Probability 1/2, it's a bad pivot. I'll just assume I don't make any progress and I'm still stuck with n. Of course, it's probably less, but I'm just being conservative. So it comes out, to something strictly less than n, 7/8 n. Okay, and that applies, for later things, except it's just conditional on how many are left. You're always still going to throw out 7/8 of the remaining elements on average, right? So if there's like 100 elements remaining in xi minus 1, but you're still saying, okay, I have 1 in 2 chance of picking out of the middle 50, and you'll get something like this. So this should be xi minus 1. Okay. Let me just keep going through this. So each time you're expecting to go down by 7/8 factor. And if you unroll this, which I think is done for us, right? You keep unrolling this. I'm looking at expected value of xi, and we do our iterative expectations. I know I'm going a little bit fast. Xi conditional in the previous one. The previous one is 7/8 xi minus 1, whatever that is, and then you apply induction. Okay, so you're just unrolling like you would. It turns out the expected value doesn't change anything. If there was no expected value, this unrolling would be obvious. Okay, good. So let me finish. We're almost done. So if you pick 32 log n or something, this is where 32 came from, and you just plug this in, 1 minus 1 over 8 to the k. Okay, here's one thing you have to know. This is the most important inequality in the world. Okay, 1 minus x is always less than or equal to e to the x. 1 plus x is less than or equal to e to the x. So you just put this 1/8 in the corner. This is true for all x, positive or negative. And you say, okay, what do I need to make k to make this small? Well, I do 32 log n. That'll work. And you'll get something like this. Okay, so the expected value is really small, like 1 over n cubed. And then finally, almost done. Sorry, I didn't time this very well. We're finally going to use Markov's inequality. The probability of lasting at least k rounds. The probability that xk is at least 1, but xk should be less than 1 over n cubed on average. So Markov's inequality says, oh, if you're at least 1, you're like an n cubed factor bigger than your expected value. That's really unlikely. So That's most expected value of xk. That's n1 over n cubed. Okay, so we use some of those tools that I introduced last time. I introduced them, I mean, I kind of used them a little quickly because I didn't time this very well. Okay, but ultimately the components were individually not too bad. So maybe take a second look at this later because maybe it's the first time to see something like this. And that is it. That's n log n with high probability. And I'll have some new applications next week after the apocalypse, if we're still alive, to further demonstrate this. Okay, so next we'll do one lecture about amortized and another lecture about randomized. The goal is to just pick topics that'll give you more practice, but at least we've covered each topic a little bit, so you'll be able to do the homework. Okay, and I think we only have one more homework after one that's currently out about these topics. So we're almost done. Okay, thanks guys.